If Saturn were to shift its orbit by just 1%, the solar system could descend into chaos. Out there, more than 1 billion kilometers from Earth, exists a colossal sphere of gas over 120,000 kilometers wide. A planet large enough to contain more than 700 Earths. But what truly concerns scientists is not its size. It is its role in the fragile stability of the entire planetary system. Saturn does not merely orbit the Sun. It drags the trajectories of other worlds with its immense gravitational pull. Its mass is 95 times that of Earth. Its composition is primarily hydrogen and helium, but it is far more complex than a simple ball of gas. Spectroscopic analysis shows hydrogen makes up about 96% of its molecular composition, helium about 3%. The remainder includes methane, ammonia, water vapor, ethane, phosphine, and trace organic compounds. Isotopic ratios such as deuterium to hydrogen, helium-3 to helium-4, and nitrogen-14 to nitrogen-15 provide clues about the early formation of the protoplanetary disk 4.5 billion years ago. Comparisons between Saturn's isotopic signatures and Jupiter's suggest they may not have formed at the same original distances from the Sun as where they reside today. Beneath a cloud layer roughly 300 kilometers thick lies a region of liquid hydrogen. Deeper still, under pressures of millions of atmospheres, hydrogen transforms into liquid metallic hydrogen. This layer conducts electricity. It generates the enormous magnetic field that surrounds the planet. But Saturn's magnetic field is strangely unusual. It is almost perfectly aligned with its rotational axis, nearly no tilt at all. A rare phenomenon for a planet with an internal dynamo. This near-perfect symmetry made determining Saturn's exact rotation rate extremely difficult for decades, and that unusual alignment forced scientists to revise interior models repeatedly. Saturn's magnetosphere stretches millions of kilometers into space, interacting violently with the solar wind. Plasma within this region does not come solely from the Sun, but from Saturn's own moons. Enceladus ejects water vapor and ice into space. These molecules become ionized, forming a rotating plasma torus around the planet. That plasma interacts with the magnetic field, generating electric currents, electromagnetic waves, and directly influencing the structure of the rings. Saturn's rings are not harmless drifting ice. Their particles are constantly bombarded by high-energy electrons and protons. Radiation within the magnetosphere alters the chemical structure of the ring particles' surfaces, creating complex compounds. Some of this material is pulled into the upper atmosphere, modifying atmospheric chemistry. Measurements during Cassini's Grand Finale phase, when the spacecraft dove between the planet and the rings, revealed that far more material was falling inward than previously estimated. And that is when the staggering number emerged. The total mass of the ring system is estimated at about 1.5 times 10 to the power of 19 kilograms. It sounds immense, yet it is roughly equivalent to a medium-sized icy moon, which means the entire magnificent structure may have formed from a single satellite torn apart by tidal forces. A cosmic accident. A moment of violence frozen into orbit. But Saturn's most unsettling role lies in orbital resonance. Saturn and Jupiter are currently near a 5-to-2 resonance. For every 5 orbits Jupiter completes around the Sun, Saturn completes nearly 2. In the past, they may have been locked in a 2-to-1 resonance. When two gravitational giants synchronize like that, their combined pull sweeps through the primordial disk, scattering billions of objects inward, a cascade of impacts, an age of destruction. If that resonance were to shift again in the distant future, the present stability could fracture. a slight phase drift, a tiny accumulated error over hundreds of millions of years. The orbits of rocky planets would oscillate, asteroids would be deflected, comets from the Kuiper belt would be destabilized. Not science fiction, orbital mechanics. There is another factor adding to the unease. Saturn's axial tilt is about 26.7 degrees, similar to Earth's. Recent studies suggest this tilt may be the result of resonance interactions with Neptune. As Neptune's orbit slowly evolves, it can gravitationally tug on Saturn's spin axis. Some models have proposed that the hypothetical Planet 9, if it exists in the outer solar system, could also influence this long-term evolution. If a massive undiscovered planet truly resides at the system's edge, it may have helped shape the dynamical architecture we observe today. An undefined variable, an unknown capable of reshaping the equation. And when we compare Saturn to the thousands of exoplanets with similar mass discovered around other stars, the contrast becomes even stranger. So many Saturn-mass exoplanets orbit extremely close to their parent stars, completing a full orbit in just days. Some are so low in density they are called superpuffs. Others have atmospheres being violently stripped away by stellar radiation. Compared to them, our Saturn occupies a relatively safe position. Safe, for now. Because this entire stability depends on a delicate balance of mass, distance, and gravitational resonance. If one component shifts, if one orbit drifts, if a hidden planet at the system's edge truly exists and migrates, the domino effect begins, slowly, but irreversibly. Saturn spins silently in the darkness, its rings stretch thin as paper across space. Through a telescope, it appears calm. But within and around it lies a web of invisible forces holding the entire planetary system together. A colossal gatekeeper. And if that gatekeeper falters, everything will tremble. No one has ever seen Saturn's core. But we know it is trembling. Gravitational data gathered during Cassini's final orbits revealed that Saturn's gravity field is not perfectly smooth. There are subtle oscillations, delicate phase shifts, and from tiny ripples within the ring system, scientists have been able to hear the planet's internal pulse. This method is known as ring seismology, where internal oscillations inside the planet generate density waves that propagate through the icy rings. The results were startling. Saturn's core is not a neat, solid sphere. It may be a fuzzy structure extending up to 60% of the planet's radius, a vast region where rock, ice, and metallic hydrogen are mixed together. No sharp boundary, no clean edge, more like a mass gradually dissolving into itself. That implies its formation may have been far more chaotic than earlier models predicted. Deep beneath the pale yellow cloud tops, pressure rises to millions of times that of Earth. Temperatures reach tens of thousands of degrees. Metallic hydrogen flows like an invisible glowing ocean. Within this electrically conductive fluid, convection currents generate the dynamo that produces Saturn's magnetic field. But unlike Earth, the boundaries between Saturn's internal layers are not perfectly stable. Evidence suggests compositional stratification, regions where helium-rich and helium-poor layers slowly separate over time. Helium is sinking. Droplets of helium condense and fall into deeper, hotter layers. As they descend, they release gravitational energy in the form of heat, a rainstorm lasting billions of years. This process is what causes Saturn to radiate more energy than it receives from the Sun. But helium rain is not just a thermodynamic curiosity. It directly affects density structure, internal wave propagation, and the planet's global oscillation modes. Those oscillations have periods ranging from tens of minutes to several hours. They travel like sound waves through an ocean of metallic hydrogen, and every subtle vibration leaves a signature in the structure of the rings above. A giant planet resonating in the silence of space. Above those deep layers lies a complex, multi-layered atmosphere. Infrared and microwave measurements show that ammonia, methane, and water vapor are distributed unevenly across latitudes. In certain regions, ammonia is depleted deeper than expected, suggesting strong vertical convection transporting material through the atmosphere. The clouds are not composed solely of hydrogen and helium. They consist of ammonia ice crystals, ammonium hydrosulfide, and possibly water at greater depths. These cloud layers stack like atmospheric geology. Winds reach speeds of up to 1,800 kilometers per hour at the equator. Jet streams create alternating bright and dark bands. But beneath that relatively ordered exterior lies a convective system extending thousands of kilometers downward. A small imbalance in energy can trigger a planet-wide storm. Radio measurements have detected bursts associated with lightning activity. Lightning on Saturn is thousands of times more powerful than on Earth. The energy released in a single strike can equal multiple small nuclear bombs combined. There is no liquid water ocean like Earth's, yet deep convection in water and ammonia-rich layers can generate enormous electrical charges. Charge builds, discharges, repeats. There is another factor rarely emphasized: chemical evolution over time. Ultraviolet radiation from the sun breaks apart methane in the upper atmosphere, forming more complex hydrocarbons such as ethane and acetylene. These molecules gradually settle downward, altering composition with altitude. This photochemical process changes the atmospheric coloration seasonally and in response to solar activity cycles. A dynamic chemical system in constant transformation. When compared to exoplanets of similar mass orbiting close to their parent stars, the contrast becomes even sharper. Many warm Saturns out there have atmospheric temperatures exceeding 1,000 degrees Celsius. Molecules dissociate. Supersonic winds blow from the day side to the night side. Some planets are so low in density that they expand to nearly 1.5 times Saturn's size despite having similar mass. Our Saturn is colder, more stable, but not immutable. Over hundreds of millions of years, internal stratification, helium depletion, and gradual gravitational contraction will continue to reshape its interior. The planet's radius may shrink very slowly. Its average density will increase, so slowly that humans cannot perceive it. But on cosmic timescales, it is unmistakable. A giant sphere of gas does not remain static. It evolves. It restructures itself from within. And every internal change, however small, influences the gravity field, the interactions with its moons, and the delicate orbital balance of the entire system. Nothing in the solar system is completely still. Saturn is vibrating, contracting, raining helium in the dark, and each oscillation is continuing the story of a planet that has never truly been at rest. Our solar system appears stable, but that is only an illusion created by the brief slice of time in which humanity exists. Saturn is part of that delicate balancing mechanism, a colossal gear in a gravitational machine that has been operating for 4.5 billion years. And history shows that when this gear shifts, everything else trembles with it. In the early era of the solar system, the gas giants did not remain in their current positions. They moved. They drifted. They interacted gravitationally with one another. When Saturn approached a strong resonance state with Jupiter, the combined pull of these two massive worlds destabilized the orbits of smaller bodies. The asteroid belt was stirred violently, Icy objects from distant regions were hurled inward. The result was a meteor bombardment that lasted hundreds of millions of years. From the surface of the moon still preserves that era like a graveyard of impact craters. Earth shared the same fate, but geological activity erased most of the evidence. Early life, if it existed then, may have been wiped out multiple times. One resonance shift. One age of destruction. Today, the system appears calm, yet precise measurements show that Saturn's moons are drifting outward faster than older predictions suggested. Just a few centimeters per year, a number so small no one could feel it. But over hundreds of millions of years, that becomes thousands of kilometers. As distance changes, resonance changes. As resonance changes, tidal energy changes. A stable system can slip out of balance without immediate notice. Farther into the future, when the sun exhausts its core hydrogen and enters the red giant phase, everything will change on a massive scale. Radiation will surge. Stellar winds will intensify. The sun will lose mass as it expels material into space. As central gravity weakens, planetary orbits will expand. Saturn will drift farther away. Colder, darker. The icy rings, already fragile, will endure stronger radiation and greater thermal variation. Their delicate structure could be completely disrupted. The moon system will undergo new orbital adjustments as the central gravitational force declines. The system will restructure, not in thousands of years, but in billions. Eventually, the sun will collapse into a white dwarf, a small, hot core glowing faintly in the darkness. At that point, Saturn will remain a frigid gas giant orbiting the remnant of a dead star. No more golden brilliance, no more luminous reflection, only darkness and inertia. Yet before that distant future unfolds, humanity may have advanced much further in exploring Saturn's domain. Titan, Saturn's largest moon, possesses an atmosphere 4 times denser than Earth's. Lakes and seas of methane spread across its surface. A functioning climate cycle drives hydrocarbon rain, river flow, evaporation, and condensation. Gravity there is so weak that a human wearing the right suit could fly with artificial wings. But it is no paradise. Temperatures near -180 degrees Celsius, alien chemistry, high pressure, signal delays exceeding 1 hour round trip. No immediate rescue, no room for error. Enceladus is even harsher. Beneath its thick ice shell lies a salty ocean that may host heat and chemical conditions suitable for life. But reaching it would require drilling through tens of kilometers of ice in an environment of radiation, extreme cold, and irreversible biological contamination risk. A single mistake could destroy evidence of extraterrestrial life before we even recognize it. The risks are immense. The reward is greater. Because discovering even the simplest biological signature would completely transform how we see our place in the universe. And all of those possibilities exist because of a gas giant turning quietly out there. Saturn is not a place humans can stand upon, but it may be the key to unlocking deeper understanding of the origin, evolution, and fate of planetary systems. Through a small telescope, it appears as a tiny golden point with delicate rings. But in reality, it is a massive body participating in the gravitational web that keeps the solar system stable. If that web changes, if a resonance drifts out of phase, if long-term evolution crosses a stability threshold, the effects will spread, silently, accumulating irreversibly. We are living in a moment when everything remains balanced, a rare moment in the multi-billion-year history of a star system. And perhaps by understanding Saturn, understanding gravity, resonance, and the fragility of stability, we may better understand our own future. If you believe the solar system is permanent and unshakable, share your thoughts below. And in your view, should humanity focus first on exploring Titan or Enceladus?